Good morning, or afternoon, or evening, wherever you're watching this. Welcome to week 12. This is formerly the last topic that we will cover trees. I think I mentioned that. So that's going to cover this week's lecture, this basically 2.5 hour lecture that I'm about to present, probably be shorter. Next week, I'll present you with, let's have a look at the time frame. The courses end this week. Okay, I'm not giving you anything new in week 13. We're in week 12 right now. That's 10, 11. That's right, 12. So you'll have just two videos I'm going to show you on computational complexity and Turing machines. You have to know what a Turing machine is at some level in your career's undergraduate degrees. This is just going to be a review at the end here. Nothing new. I don't like to overload people just before final exams, although our final exam is all the way up, I think, on the 22nd. The 22nd. So your final exam's way up here. So you got a month before the final exam. That's wonderful for you. That's great. So, and let me start by showing you something from ChatGPT. I just pulled up, okay, prove the handshake theorem in several ways, including induction. So, this, I believe, is a nice way to show you, the basic kinds of approaches that there are to proofs in not only graph theory but trees. So this is graph theory. We talked about this handshake theorem last week when we talked about graphs. So there's the intuitive counting proof. Okay, each edge has 2 points. That's the handshake theorem. When you sum degrees, every edge contributes. So one to the degree of one endpoint, one to the degree of the other endpoint. So it has to be exactly two in total. Sum of degrees. Okay. So therefore, sum of degrees, that's supposed to be an equal 2 times number of edges. Looks like minus. That's the whole idea. Proof by double counting. I've seen this where we're counting edges and nodes. Okay, we're double counting nodes and edges. Okay, so first of all, here we have that the degree of the vertex, the sum of the degrees of the vertex is 2 times the um, cardinality of the edge set. Here we have S, okay, which is basically the same thing. Uh, okay, they call it S here. Now count the set of incident vertex edge pairs, okay? VE, V is incident to E. For a vertex V, it contributes degree V pairs, total S. Fix an edge E, it contributes exactly 2 pairs, its endpoints, total 2E. So both count the same set, S and 2 times the cardinality of E. So that's double counting. That's nice using the edges and using the vertices. Now, induction is a different story. Look at it. It's there's more to it. This is when all else fails. You use induction. The other methods are totally acceptable. A base case, okay. If there's zero edges, then all degrees are zeros. It's the trivial solution. 2 times the edge set equals zero. That holds. Inductive hypothesis, we assume this is true. The inductive step, we want to get the k plus first step from the kth step, okay. And so what do we have here? 2k plus 2 equals 2 times k plus 1. So that's basically what we're doing now. Add the edge back. So the graph with k plus 1 edges, remove one edge, E. That's what we always do, removing or adding edges, removing or adding vertices. So we build things up from the trivial case. Remove an edge, new graph has k edges, okay? By hypothesis, this is true. Now add the edge back. Degree of u increases by 1, no doubt about it. Degree of v increases by 1, so total degree increases by 2. Therefore, yes, it holds. The conclusion is that's fine. We did not do strong induction, starting with one vertex. Oh, I thought it said strong. So this is induction, a different approach where we start with one vertex and build up, okay? Base case, one vertex, just like before. Build the graph step by step. Construct any graph by adding one edge at a time. Each time you add an edge, you increase the total degree by exactly 2. So there, proven constructively, as they say. We forget about the adjacency matrix. There's a corollary, big deal. So that's pretty good. That's a very good summary. I would look at that if I were you. It's not written in your textbook so clearly. I haven't presented it as clearly. For material like this, this is all correct. I've double checked it. The ChatGPT is very useful as a pedagogic tool as long as you don't rely on it too much. Here, in this case, this shows you, it summarizes the various ways that you can approach proving the handshake theorem. That's very useful. That's a constructive use of ChatGPT. But using it and just memorizing these proofs is not. I just wrote a piece in my textbook, and I have a graph to show what happens. Maybe just give me a second. I'm going to show you. Okay, it's right here. Let me pause it for a second. Okay, here's a graph I've come up with for a book I'm writing, and that's not that. Oh boy. Okay, how do I get it? Okay, how do I get it? There it is right there. So, effort, understanding, trade-off. You've all heard of the point of diminishing returns. So this is effective cognitive effort. Sorry, I should say understanding epistemic access. I don't know if you know what that means, as a function of effective cognitive effort. So, for example, back in the old days when I first started, we used punch cards. Eventually, punch cards turned into a different way. Basically, terminals came along. Terminals was a big jump forward. And still at that time, we had to build our own routines. There weren't libraries back in the beginning, and very few of them, at least not for the academia and the general public. The military certainly had them. But having a plotting routine made for you in a library, it offloads, the trivial kind of work needed to solve a problem. It doesn't take away from your understanding of the problem. Okay. And we got APIs eventually. We kept getting better at being able to code these problems. And then all of a sudden, ChatGPT comes along. Okay. Now, for example, I plugged in. I think I told you this in the beginning. I plugged in one of my hardest um, AI problems in Compute 310, which was a 2-month long group project. I just plugged it into ChatGPT and it gave me the answer, and it was correct. And it had the right references. It's quite impressive. But guess what was lost? I'm over here now. I'm over here and trying to figure out what I actually did. That's the point of diminishing returns. That's what you have to think about. Okay, I don't mean to harp on this so much, but you have to learn to use it wisely. This is an amazing tool. It's a fantastic text editor. It's a great editing device. You just watch it carefully because it does make a lot of mistakes, especially if you don't have the plus version, which I don't. I refuse to. They ripped me off last year when I bought it and thought I was having service, and I wasn't. They wouldn't even reimburse me. Anyway, regardless of that, the free version is still good enough as long as you monitor it, and it's good that way. I prefer it. I prefer it making mistakes because it forces me to read what it gives me. It forces me to go through the calculations that I've asked for because it does make a lot of mistakes. But this is the point right here that, this is the point of diminishing returns. The moment you've had this 2 order of magnitude jump in your ability to solve problems. So I've got these routines, these APIs, all these things that help me code up a problem to address some kind of physical problem, a physical system I'm modeling. All of a sudden, I make this jump where I'm abstracted away from the nuts and bolts of the problem, and quite frankly, that's not a good thing. It's kind of like these inferential statistics, these inferential models that they use in climatology or in wet meteorology. Sure, they have their value, but there's no physics in them at all. It's all based on statistics. and you're missing something. If it works, that's good. I'm for it. If it's used alongside simulations that have the physics in them, do not move away from the foundations, from the first principles. And that's what I'm afraid most people are doing. Okay, that's my spiel. So make sure you pay attention to that. Let's go to this final presentation now. I hope you appreciate what I told you. Which means you have to do the work. And I know we're lazy. Geez, I don't have much time to hand this homework in, and just let me, use ChatGPT to at least give me a hint. That's not bad, but to just copy and paste, or if you have the solution key, you're just only screwing yourself. Pardon my terminology. So here we go. What kind of a tree is that? Some human-induced tree. That's for sure. So what are we going to do? Remember we talked about graph theory before. So we're going to go back to definitions again. I'm going to go over what we did in graph theory again, just to drive those points home. Properties, to understand what properties of a relation are required for it to define a tree. That's a weird sentence. To learn the basic formula for counting internal vertices, leaves, and edges of a tree. To learn the basic formula for determining the height, depth of a tree. Height and depth are two different things. So, graph theory review. So, informally, graphs are mathematical structures used to model binary relations. Don't forget that. That's what a graph is. Fundamentally, it is a mathematical structure used to model binary relations. So, it's a natural next step past relations and functions. Between elements of a given set and are central to data structures. Of course they are. Data structures relies very heavily on this. Graph terminology in chapter 10. We also introduced the idea of digraphs already. So basic concepts, just look, I don't want to go through this again. We talked about this last week, so make sure you understand these definitions. Parent, child, sibling, ancestor, descendant, degree. Okay, I mean, come on. Degree of a leaf is always one because a leaf is an endpoint. So it only has one branch going into the node that has no other branches or edges coming out of it. So that's what a leaf is. A leaf is like a file in a directory structure that's got a tree architecture. So, these are all obvious, these things. You can read them. We're going to go through it again. Path. This is good now. A sequence of edges connecting two vertices. So length of a path, number of edges. Height of a tree, the length of the longest path from the root. Like the root always starts at the top. As a binary tree, it goes into two. Those two go into two, and so forth. So it's exponential in its growth. You have a certain depth down there. The number of nodes is 2 to the d, where d is the depth. Height of a tree. Okay, depth of a vertex, number of edges from the root to that vertex. So here it's edges. You have to be careful. They're talking about edges for the path right here. All of this is edge dependent. Depth of a vertex, number of edges. Level, all vertices with the same depth. Paths and distances. Okay. Now, paths and distances. Many graphs theory introductions, the word path implicitly means a simple path, unless otherwise specified. Because of this, textbooks or lectures may not always list simple paths separately, assuming the audience understands that paths don't revisit vertices by default. So a simple path doesn't visit vertices more than once. Simple path. Potential confusion with walk and trail. Graph theory distinguishes among walks, trails, and paths. We just talked about paths. A walk can repeat vertices and edges. A trail, no repeated edges, but can repeat vertices. Path, no repeated vertices. Simple path, no repeated vertices. Okay? So make sure you know this. This is extremely important. Because of this hierarchy, sometimes path is used synonymously with simple path, as we just said up there. Now, special trees. Binary tree, it has a branching factor of 2 forever if it's a full binary tree. Just a binary tree, it means the maximum number of edges coming out of a node is 2, but it doesn't have to be 2. It can be 1 or 0. So a full binary tree is one Each children has either 0 or 2. Each vertex is either 0 or 2 children. So obviously that's a leaf. A leaf has 0 children. Maximum of 2 because it's binary, so that means it can have. All right. Complete binary tree. All levels are fully filled except possibly the last, which is filled from left to right. Spanning tree, a subgraph of a connected graph. A subgraph, okay, we'll talk about those, show you examples, which induces all vertices and is a tree. Well, sorry, includes all vertices and is a tree, but it's a different way of connecting the vertices. Minimum spanning tree, a spanning tree with minimal total edge weight. We'll see what this means shortly. So, miscellaneous terms, edge, you know what that is. A parent edge, child edge. A subtree, tree consisting of a vertex and all its descendants. Well, so for example, if you have a binary tree, you have a binary tree. All right. So here's a binary tree. Right? Here's a binary tree. And if we go back to what we're talking about here, all right, this is a subtree. All right. Subtree, a tree consisting of all vertex and all its descendants. That is a terrible definition because what we mean really comes down to this is a subtree, this is a subtree, this is a subtree. No matter how far down it goes, it just starts at that node as the root node. This is the master root node. I don't call it master. I do. I just did. But here's a subtree. Okay, you get the idea. You get the idea. Binary search tree. Okay, so we have a binary tree where the left child is less than the parent, which is less than the right child used in computing. So binary search tree is exactly that. It's a decision tree. Binary, true, false, 0, 1, yes, no. So binary search trees are fundamental to computing science. Here we've seen this already, okay? The fact that the edge set is a Cartesian product of the binary relation V cross V, the vertex set with the Cartesian product with itself. Okay, so that's the edge set. We know what the vertex set is. Say it's a directed graph on a digraph where V is the set of vertices or nodes and E is the set of edges. So this is how we write it. I've mentioned before in set theory that set theory unifies all of mathematics. They looked during the 20th century for a long time for a way to unify all of mathematics. They thought functions would work, and they came up with the lambda calculus. All these things failed in comparison to graph theory. Set theory. Set theory underlines everything, so you see how we define things with sets. We've seen this already, okay? We've seen this. This is just okay, digraph informal definition. A non-empty set of vertices, a set of ordered pairs E from the Cartesian product of V with itself. Okay, it's a directed edge. You can see it goes from U to V. That's a directed edge. If it goes both ways, it's not a directed edge. Okay, so undirected, you can go either way. Directed, you can only go one way. No big deal. Digraph formal definition. All right, so this is not saying anything new here, that's for sure. Not saying anything new here. We've seen this already. This is from the other textbook, Grimaldi. We talked about this already in the former presentation on graph theory. And we talked about multigraphs and how it related to the Königsberg problem. There's vertices A and B are endpoints of an edge. We say that they are adjacent and write A squiggle or tilde B. If vertex A has one of E's endpoints, A is incident to E, and we write A epsilon E, okay? We're not going to do any of this in this class. This is for advanced graph theory. Don't worry about it. A walk is a sequence of vertices. That's pretty good. A path is a walk where these two are not equal to each other. In other words, a path is a walk that visits each vertex at most once. So a walk is just a sequence of vertices. A path is a sequence of vertices in which you don't use one vertex more than once. A closed walk is a walk where V1 equals Vk, so it's a cycle. A cycle is a closed path, i.e. a path combined with the edge Vk, V1, so the first and last connect back up again. A graph is connected if there exists a path between each pair of vertices. So you can go from one vertex to any other vertex in the graph. That means it's connected. Don't forget that. A tree is a connected graph with no cycles. That is one definition of the many ways of defining a tree. You know what a forest is already. It's just a bunch of partitioned graphs, okay? Partitioned trees, okay? So now we'll talk about trees. So here we go again. We've seen this already. I don't know why it's here again. I have to amend this. Oh, because here I say the size of the graph is the number of vertices. Oh, this is out of place, that's all. So this should have followed here. Okay, that's what I did wrong. I put this in the wrong place. Okay, preliminary terminology. Here we go again, back to walks, okay? XY, not necessarily vertices, an undirected graph. An XY walk in G is a loop-free, finite alternating sequence. X goes from 0, edge 1, x1, edge 2, x2, etc. Consider any XY walk in an undirected graph. If no edge in the XY walk is repeated, then the walk is called to be an XY trail. What a bunch of stuff. You've got to just write it down and memorize it. You should all write it down on a piece of paper somewhere. And don't forget, sometimes there are inconsistencies. Some people mess up these terms, mix them up. A closed X trail is called a circuit. So we have a circuit now, this idea of a circuit, and we talked here of a cycle. Where is it? Where did we find that? A cycle. So we talked about a cycle already. A closed walk is a walk where V1 equals Vk. A cycle is a closed path, one where the first and last edge vertices are connected by an edge. So that's a cycle. If no edge in the XY walk is repeated, then the walk is called a trail. A closed trail is a circuit. When no vertex of the XY walk occurs more than once, the walk is called an XY path. The term cycle is used to describe a closed XS path. So you've got circuit and cycle. What's the difference between these? Let's find out. If no edge, okay. Where's the one I'm looking for? Up here. A path is a walk with no repeated vertices. A cycle is a closed path. A trail is a walk with no repeated edges. A circuit is a closed trail. So that summarizes what they are. But isn't this the same? Yeah, what's this doing here? What am I putting in dealing with a circuit, we shall always understand the presence of at least one edge. When there is only one edge, then the circuit is a loop. So it's a edge that goes back to the same starting point, okay? This is what I'm looking for. This is very important. Okay, both cycles and circuits are closed paths, meaning they end and at the same vertex as where they started. For a circuit, vertices may be repeated but not edges. For a cycle, neither edges nor vertices may repeat, except that the start vertex is the same as the finish vertex. Hence, all cycles are circuits, but not vice versa. Remember this. Remember this. Very important. If you really understand these definitions, then this bold sentence will make sense to you. So here you can see that the path A, B, C, D, E, F, A, B, C, D, E, F is a cycle, okay, because it goes back to A. See, its starting point is the finish point. An example of a circuit that is not a cycle would be, say, D, B, C, D, A, F, D. You can figure it out for yourself. So here we have these. I keep repeating the same thing over again just so we make sure we're consistent, we get it. Graphs as relations. Okay, an undirected simple graph can be viewed as a binary relation R on set V, where the ordered pair UV is an element of the relation R, and that means that there is an edge between U and V. That's what that means. Ordered pairs means it's an edge. For a simple undirected graph, anti-reflexive, okay, so a simple undirected graph has no loops and no parallel edges. A simple undirected graph, it's undirected, of course. If it's symmetric, that means it has, one edge going to this and another return edge, or just one line, meaning go both ways on the line. These conditions define an undirected simple graph, but not necessarily a tree. You have to have more for a tree. Trees and subforests, can anybody guess where that is? Okay, there's nobody out there, unfortunately. Well, for those that are interested, it's Whistler. So here, continuing our study, this is where it starts in chapter 11. This is right out of your textbook. Continuing our study of graph theory, we shall now focus on a special type of graph called a tree. So those of you that have taken any electronics or circuit theory, like DC circuits, LRC circuits, inductor, resistance, capacitor, hopefully you've done a little bit of that in high school physics if you've taken high school physics. There's basically the conservation of current going into any point. What comes in goes out. So these are like the Kirchhoff's laws, conservation of current, conservation of charge. Okay. And 1857, Cayley used the special kind of graphs, these trees, in order to enumerate different isomers of the saturated hydrocarbons CnH2n plus 2, where n is a positive integer. All right, that's fine. So here, Kirchhoff used it. So that's Kirchhoff. He started it off. Okay, with circuits, and then Cayley used it for biochemistry. So here you have I as the current, so I have current 1, 2, 3, 4, and 5, and currents in, that's the node, currents out. So what goes in comes out. They're the same. You can see I1 plus I2 plus I3 plus, or it should equal I4 plus I5. That's another way to put it. Here, you can see a game tree is the game tree of tic-tac-toe. And in artificial intelligence, we find ways of simplifying these things by, say, in this case, rotational symmetry. You can eliminate some of the branches just simply by rotational symmetry. What does that mean? It means that if you have this situation, that's in the middle, then putting a 0 here is like putting a 0 here, rotate it, or putting a 0 here, rotate it all the way, or a 0 here. That's rotational symmetry. So you can get rid of all three of those four branches that are coming out of the first node, the starting node. Chess, look at that. Okay, there are 20 first moves in chess. You can move. Some of you probably don't know chess. It's a board with 8 by 8. So you have pawns lined up here. And pawns, there's 8 of them, and they can either go 1 ahead or 2 ahead. So that's 16 possible moves. And you have knights, which can go over. They can go over, or this way, a pawn or any other object, one of these pieces, but they have to turn left after they've gone over them. 2 and 1. 2, 1, like that, or 2, 1. And so there's 2 of those, and they have 2 possible directions. So that's 16 plus 4 is 20. So there's 20 possible first moves. Then look at the next move in the gameplay by the opponent. And then you're the starting person, has all of these choices. This is an exponential tree. It is on the order of 35 to the depth of the thing. It is clearly intractable. This is an intractable problem. Yet Deep Blue beat Garry Kasparov because it was a IBM chip that was optimized for playing chess. It calculated 20 million moves ahead each time. It just did it by brute force. And heuristics, some heuristics were involved. So a tree is a connected, undirected graph with no simple circuits. A tree is a connected, you can get to any node, undirected graph, so you can go both ways, with no circuits, no simple circuits. Because a tree cannot have a simple circuit, a tree cannot contain multiple edges or loops. Therefore, any tree must be a simple graph. Bingo. Don't forget that. So what do we have here? Is this a tree? Is this a tree? Is this a tree? Well, this tree has a circuit, so it can't be. Look at that. So I can go from here to here, to here to here. So no, that's not. And what about this one? Well, it's not connected. I can't go from here to here or here to here. This doesn't mean that they are intersecting. That would mean there's a node there. But if there's no node there, that means they cross over each other without being able to, get into the other path. So there's a simple circuit here, and it's not connected. So don't forget, a tree is a connected, undirected graph with no simple circuits. That's good. So, because a tree cannot have a simple circuit, a tree cannot contain multiple edges or loops. Therefore, any tree must be a simple graph. We just said that, did we not? Yes, we did. All right. For God's sake. Which of the following graphs shown on figure 2? Is this figure 2? Yep. Okay. I've got to take that out. Boy. Okay, that screwed that up. So a tree is a connected, undirected graph with no simple circuits, no multiple edges, no loops. An undirected graph is a tree if and only if there is a unique simple path between any two of its vertices. Note, a graph is connected when there is a path between every pair of vertices in a connected graph. There are no unreachable vertices. So I'm repeating myself a lot in this just to get the point in. And so if you have this is a tree. Now, the whole thing's a tree. It's actually a forest because it has two trees that are both disjoint sets of edges and vertices. Okay, so these things are both trees. Therefore, that's a forest if it's part of the same graph. A graph having no cycles is said to be acyclic. A forest is an acyclic graph by definition. I mean, it has to be because you can't get from one to the other. Definition, a tree is a connected graph without any cycles, or a tree is a connected acyclic graph. The edges of a tree are called branches. It follows immediately from the definition that a tree has no simple, it has to be a simple graph because self-loops and parallel edges both form cycles, you see. So here, this is all trees with fewer than 6 vertices. That is all of them. There are no others. So with 6 vertices, that is the number, the 1, 2, 3, 4, 5, 6, 7, 8 trees that can be built. It's nice to know. Okay, yes, this is repetition. Trees as special binary relations. Okay, a binary relation R is the Cartesian product A cross A, is a set of ordered pairs. It can be represented by a digraph. Elements of A are vertices, pairs. Just so much repetition here. Okay, anti-reflexive, not a loop at all, and symmetric. Okay, a tree is a binary relation that is anti-reflexive, symmetric, meaning you can go back and forth along edges. Meaning it does have parallel edges. Symmetric edge pairs combine into a single undirected edge, producing a graph. Okay, so remember that's what anti-reflexive means. It just simply means there aren't any edges at all that exist in that graph. Tree example, given the set A, which is 1, 2, 3, 4, 5, consider the binary relation 1, 2, 2, 1, 1, 3, 3, 1, 1, 4, 4, 1, 4, 5, 5, 4. Why is there such a big space there? And so you can see that the digraph, we make these parallel edges just simply into lines, okay? A graph has no circuits and therefore is a tree. All right. I'm going to do this later on today. Okay, finish off this presentation later on today. We're a third through it. I just need to take a break, finish my coffee. But I'll be back to produce the next and final portion of this. I'll do the rest momentarily. So please let me just go for a second. Just for you, it's just typing into the next presentation. Okay, we'll see you shortly.